Again, this is the one type of the indeterminate problems. And for these problems, here there's two loads, 60 kilonewtons and 40 kilonewtons. And for this case, there's a gap here. So we want to calculate for this example is meter. This is a meter, 0.1812, 0.1 meter. And let me call this is A, this is B, this is the C, D, and E. The question is to ask what is the reaction at A and the deflection, which means the displacement at point C. This problem is very similar to one of the former problems, and in which there's no gap. So that former problem is easier than this one. For this, again, we can utilize this is our generic model. This is P, and then deformations delta equal to PL over EA for this case. So the first one we need to analyze is the distributions of the reactions in each segment. And again, for the positive, the reaction is to stretch the materials. And for the negative, that means the reactions is going to compress the material model. Okay, now for this one, we can quickly draw the reaction. And here, allow me to quickly draw the result. So in this section, AB, the force should be equal to, if you can do the calculation quickly, that should be equal to 100. And then in BC, that would be equal to 40. And the same 40 here. And then go to the final one, that's the drill. Okay. So now we can first to calculate what will be the diffraction at the end E here. If the diffraction at E is larger than the gap, and oh, I forgot to give you the gap. The gap is equal to 0.12 meter. Uh, 0.12 millimeter. Sorry, that is very small. So the first one, we simply to calculate if the gap will be closed. If closed, then we have to use the indeterminate problem strategy. If not, then we just got the answers right away. So for this case, we assume that we simply calculate delta at E, assuming that there would have no constraint at this end. So that will be coming from the contribution of 1, 2, 3, 4 segments using our templates there. For the first segment, the force is 100 kilonewtons. L is 0.18. EA, the Young's modulus is 200 times 10 to the 9th. And A is the diameter is 40 millimeters, so that is pi over 4 times 0.04 meter to the square. So the outcomes of this is because I have converted the force in terms of newtons and the length in terms of meters, so whatever. So the result should be in terms of the meter. Okay, that is in terms of unit. So that is for the first segment, and we move on to the second one. For the second one, again, we plug into the calculation PL over EA. The force is 40 times 10 to the 3. L is 0.12, and 200 times 10 to the 9th. And A is pi over 4 times 0.04 squared. Yes?
Isn't one of those sections,
Which section?
the section to the left? That one? Doesn't that one have 60 newtons on it?
We can do this one quickly.
There's 62 newtons.
So if I take the cross section, so that would be the same as here. And 60 kilonewtons applied to here. That is the action here. So on this section, this should be equal to 40.
Oh, okay. Thank you.
Okay. So now we move on to the third one. The third one, the force equal to 40. L equal to 0.1. E, for the third one, the E is changing to 105. A is also different, pi over 4. The diameter for the third segment is 0.3. And the last segment, the force equal to 0, so that is 0. And my writing, would that be too small for the gentleman you sit in the back? That be okay?
Good.
So your eyes pretty 20/20, right? So now for this case, we can calculate surprisingly, I don't have the numbers. Can anyone do the quick calculations for this? I'm waiting. And I can tell you the result is larger than this number. Okay, so here we, while someone punching these answers for us, we move on to the next strategy because the gap is closed. So that means this material okay, so that deformation would be, let me exaggerate the deformations, and this is the boundaries on the other side. So in total, this is our calculation from there. So therefore here, there must exist a reaction force, let me call RE. And this RE is going to push back the virtual displacement by how much? By this much, right? Okay, so from here, the RE is the direction at RE. So right now, my drawing is trying to match whatever the model here, and the RE is trying to push back this model by how much? By this much. This is a reference force here. And let me do a quick calculation for this because I need the numbers here. Let me begin to mess up the whole terms here. Okay, so this is 1.48 times
10 to the negative 4.
10 to the negative 4 meters. So this will be equal to 0.148 millimeter. Okay, so that means here you can see this one. This is our calculated is 0.148 millimeter, and this gap is only how much? Is 0.12 millimeter. So the RE, that is reduction to prevent this material at NE to stretch that much by how much? This would be equal to the difference between the two numbers. That would be 0.028 millimeter, right? Okay, so in this way, this is our model here. So the same thing for this one, we can calculate the reaction of RE by this. So this is the X, and this is reactions here. So for this model, the reaction will be equal to RE as L squared. The magnitude equal to RE, and the RE for this case, for this statement, is to compress the both material. To compress the both segments such that the net change here is exactly equal to 0.028. So from here we can calculate. So here you can see the deformations on one side is 0.28 millimeter. On one side, that is from our formula PL over EA. RE times L. The distance here is 0.3. Let me label it. 0.3 meters. And that is 0.2 meters. And 0.2 meters, I simply is measured from the interface to the final end. And don't worry about, again, someone, I think, kind of thinking here is a little bit disturbance, the kind of deformation. But you can see this number compared to 0.2 is very small, right? So we just approximate using the whole length. So for the first one, E is 200 times 10 to the 9, and 8 pi over 4, 0.04 meters squared, plus the second segment, RE, 0.2, 105. And again, here is the magnitude, because we know that from the description, we know that this material is going to compress. So here I focus is only on the magnitude, because the two segments will be compressed. So that is the magnitude of compression in each segment equal to the total compression here. Okay, by solving this one carefully, then RE let me convert this one. This is a unit of millimeters, 0.028 millimeter, because here the unit on the right-hand side is in terms of the meters. So here, let me convert it. That is 2.8 times 10 to the minus 5 meter. Okay, so millimeter converted into this one, 0.028. Okay, so from here we can get it. The RE reactions, we can calculate that it should be equal to 6.33 kilonewtons. The direction of the reaction is, the direction of RE is like this, push back, going in that direction. Are we okay? And in this way, what is RA? RA is this, because right now this gap, the RA is the reaction here, and this is, let me do this again. So right now this is the model, and we apply the loading 60 kilonewton and then 40 kilonewtons here, and this end actually is to press against the wall and to induce the reaction RE. So by equilibrium in the x directions, you can tell what is RA. RA should be equal to 60 plus 40 minus RE. And in magnitude, that is 93.67 kilonewtons. This is the magnitude, and this is the direction. Are we good? Any questions? If no questions, then let us move on to the second problem, displacement at sea. Displacement at sea, basically that is, we look at this one, basically that is C relative to B plus B relative to A. C relative to B and B relative to A, right? So simply the displacement of this point at C is relative to this, which is in turn relative to this, and A is fixed. So basically the C is this one. So in concept, C is formulated like this. And now we can see our original model is this. We're assuming if there would have no constraint here, then the whole model will be free to move by that much. So that means let me use the two colors to indicate the combinations. And just kind of try to build up your conceptual things. Again, the first scenario is this. If there would have no constraint here, the whole bars are free to move going that way, and that one I use red color to indicate. Here I exaggerate the deformations. Just like this. But you can see the little bit of extrusion into the wall is not allowed, and that amount actually we calculated is this one, right? And the reaction of the RE is try to prevent that protrusion is this. The RE is applied to the virtual rate deformed model by maintaining this side to the wall here. So that means the RE actually is to pushing back a little bit. Can you see what I want to say? Okay, so in this way, what is the net force? The net displacement, basically, our answer is this. As long as we can figure out this amount, that is our answer. Right? Are we good? And what is this amount? Let me do this one carefully. This is our answer. And how to calculate our answers? We do this things. The first one, we calculate this amount. what is this amount? And again, we use color code. The red one corresponding is assuming there's no constraint here, the whole thing is free to move. So this amount actually, would that be the Q term? That be right? Just think about from the very beginning. Our beginning for those formulations is assuming here we don't have the constraint, so we kind of write up this one, and that is the first segment displacement is the second one. So basically, text summation, that is the Q term given by that.